Good morning, everybody, and welcome back from our little winter vacation. Here's a reminder of some stuff we did a long time ago. We saw several definitions of the limit. This was the definition of the limit of f as x approaches a point, and this was the standard one that we discussed the most. Everybody remember? Everybody synchronized? Then we had some variations of it. So we had this one-sided limit. This was the definition of the limit as x approaches a from the right. And then you can write the similar one if you put a minus as x approaches a from the left. It's very similar, except that now the delta neighborhood is only a right neighborhood of a. Remember this? And then the last thing we did was the definition of the limit as x approaches infinity. Okay? And there, the entire concept of being close to a point was somehow replaced by being close to infinity, and we can no longer say a neighborhood of infinity, and what replaced that is a neighborhood in the sense that we start at bigger and bigger and bigger m's. So if you go beyond m, that means you went closer to infinity, then f of x minus L is less than epsilon. So does everybody recall these definitions? Okay. And we saw various theorems. We saw the Sandwich Theorem. We saw limit arithmetics. We saw some theorems that discuss the absolute value of f. How does it relate to to f itself in terms of the limit? We saw a theorem that discussed a bounded function times a function that tends to 0. We saw various theorems, and we discussed most of them for this first concept, and then we said that variations of them hold just by very small modifications for these two. Okay? And although we are not using these definitions with their full power. We're not proving everything. We're not. We're only introducing them and kind of getting familiar with them. I think that by now you already figured out and have the feeling that these are not easy, right? They're challenging. Do you agree? Or am I the only one that feels like that? Okay. So what I want to do now is put another bullet, except it's not going to be here, it's going to be on the next board, and define another situation which we didn't handle yet. And let's see if you can, based on these, somehow figure out what the definition should be on your own. So what I want to define now, the picture to go along with it, is the following picture. Suppose we have, so this is x and this is y, and suppose we have, for example, the function 1 over x squared. Do you remember what the function 1 over x squared looks like? Right, exactly. So some people are doing this with their hands, and that's true. And please print those pages with the functions. When I say 1 over x squared, you should automatically see this, everybody. That's very important in this class. So here is 1 over x squared, just a sketch. Okay, so this is 1 over x squared. When x goes to infinity, what's the limit of 1 over x squared? 0. That falls under the last bullet in the previous bullet. We can also say that when x goes to minus infinity, over here, 1 over x squared goes to 0. I didn't write that, but that's again a modification of the last bullet in the previous bullet. Do you agree? But what I want to discuss now, and this we didn't do yet, is what happens to 1 over x squared as x tends to 0. Okay? At 0 itself, this function is not defined. That's the one thing the definition of the limit doesn't care about. Remember? But what happens to the function as x goes to 0, as we get closer and closer to 0? And what is the intuitive answer? Right. We want to say this. We want to say, so we want to define, so here's the definition. The limit of f of x as x goes to a point, a. Here a happens to be 0, but that's just in this example, equals infinity. That's what we want to define now. And when does that happen? When does that happen? So I want you to try. Keep an eye on the previous board and try to... What do you expect me to write here?
Delta bigger than 0, or epsilon bigger than 0?
Okay, so for every epsilon bigger than 0, right? That's how all the previous definitions started, right?
Right, there exists.
Wait, before you continue, I claim it's wrong.
It should be f of x greater than...
What was the role of that epsilon? It meant take an epsilon neighborhood of the L, right?
Oh.
But now, oh, very good. I like that. So, oh, but L is up there, right?
L is bigger than L.
Okay, not almost. You're getting there.
F of x is bigger.
Not f of x.
L. F of x minus L. Epsilon.
Okay, so don't just throw epsilon, f of x. We want to say that somehow the values are getting closer and closer to infinity. We had that phenomenon, but that phenomenon we had on the x-axis when x went to infinity. And how did we capture it?
X is bigger than M.
X is bigger than m. So the statement was there was an m, right? And then we said, okay, if x is bigger than m, then blah, blah, blah. This is exactly what we want to do here. We want to have an m, except we want it to live on the y-axis, and later we're going to say f of x is bigger than m. Okay, so that's how it starts. For every m, think of m up there, and then what? How do we take a neighborhood in which this limit process, remember it's dynamics. How do we find a neighborhood in which the limit process holds?
X minus A exercise between delta and 0.
Right, it's going to be the good old delta. Do you see that? Okay, the delta is going to be just like before. So for any m, there exists a delta such that if x minus a in absolute value is less than delta and greater than 0, that implies what?
F of x is bigger.
Exactly. Very good. Does everybody agree? Give me an m. You want to say this goes to infinity. So the way to say it is, if you're close enough to 0, the values are bigger than 1,000,000. So take m to be 1,000,000. It's up here. Do you see 1,000,000? Exactly here. See it? Bless you. So take m up here. Maybe let's write that. Here's m. If you want to guarantee m, if you want to guarantee that the values of the function exceed m, you need to be, if you take this neighborhood, they're not going to exceed m. But if you're close enough to 0, how close? Maybe this close. If you're close enough to 0, all the values here in this neighborhood, so this is 0 plus delta and 0 minus delta, all the values here are going to be greater than m. Do you see that? And what's the key word in the definition? For any, exactly. So this works if you want m to be a trillion. There it is. Here's a trillion. You can find a small neighborhood for which the values exceed a trillion. And so on. Okay, what's the next biggest number that you know? Trillion and one. I like that. Google. Heard of that number? It's not Google the search engine. It's Google, or I don't know how to pronounce it, but it's, I think it's 1 with 100 zeros. That's big. Almost as big as the US deficit. No. Okay. So, is this clear? Is this definition clear? Question, yes.
Why is the delta necessary? I mean, if we just define for any n that there is f of x greater than n, then we're also done.
No, but so the question was, why is delta necessary? Why can't I just say, if for any m, f of x is greater than m? For which x's? You want to somehow, the phenomenon, the dynamics you're trying to capture is that when you get closer and closer to 0, the values get bigger and bigger. It's of course not going to be true that the values of the function are always greater than 1,000,000. They're not. Look here. Only when you're close to 0, you get that. Okay, that's the dynamics. And I want to point your attention to the fact that even though on the previous board we had all these definitions that we already discussed, and you were peeking at them as we tried to put this on the board, it was again challenging. Okay? So these definitions take time to work with and to get used to. Okay? And that's okay. And in this course, we're only doing it to a certain extent. Okay. So let's do several things. I want to prove one example by definition, just for the flavor, to remind you what those look like, and that's going to be the last example I'm ever going to prove of a limit of a function by definition. Let's prove this. So I want to prove, example, I want to prove this. I want to show that the limit of 1 over x squared as x goes to 0 is infinity. So how do I prove it? How do I start? Try to remember what we did in the epsilon definitions. Right, but there's no epsilon here. For any m. So that's how we started. Let epsilon be greater than 0. Let m. That doesn't sound like good English. Let m, right? But there's no, so maybe write take m. The m doesn't necessarily have to be positive, although eventually it's going to be, right? Because for any m, this should be true. Take m. What do we want to show? What do we want to show? That f of x is greater than m. That's what's written there, right? So we want to show, maybe let's make a little cloud of how we think, right? Cloud. This is my thoughts. And then we'll formalize it. Okay? So we want f of x greater than m. What's f of x? 1 over x squared greater than m. That's what I want. That's not going to always be true, of course. It's only going to be true when I'm close enough to 0. Do you agree? So I somehow need to play with this to move things around, and delta is going to appear. And this is how I do it. So what guarantees that 1 over x squared is greater than m? That would happen if 1 over m is greater than x squared. Do you agree? And that would happen if, all this is just my thoughts. I'm not formalizing it yet. So this would happen if x itself is less than 1 over root m. And maybe I should take this in absolute value, because it could be on both sides. Do you agree? Do you agree that if x in absolute value is less than this, square it, you get this, cross multiply, you get this. Do you see that? So this is what I want. So what's my delta? This is my delta. Take m, or I'm going to rewrite this. I know what the word I want is. So given m, somebody gives me an m, take delta to be 1 over the root of m. So let's assume that m is positive. Otherwise, this doesn't exactly compile. If m is negative, just take a bigger m than it. And if you exceeded that bigger m, of course, you exceeded the negative m, right? So you can always replace a non-negative m with a non-positive m. Just take a bigger one that's positive, and you'll do the trick. You could. Would be an equally good way to write it. So take delta to be this. Then, if x minus 0, right? 0 is my a here. If x minus 0 in absolute value is less than delta, if x minus 0 is less than delta, which is the same as writing x is less than delta, which is the same as writing x is less than 1 over root m. So if this, then x in absolute value is less than 1 over root m, and this implies that 1 over x squared is greater than m. And this implication follows from this cloud. Let's take Pinky out of the way here. Good? Do you see the definition hiding here? Given m, you need to take a delta. If this, then this. Do you see the core of the definition of the limit in this statement? Yes?
Why is that x minus 0?
The 0 is the a in this example. That's the point we're approaching in this example. In general, it can be any point a. But here it's 0. More questions? Okay, so this is just an example, but this is the dynamics, the phenomenon that we want to capture and formalize, and that's how we do it. Now, I want you to do the following. So EX stands for example, but it also stands for exercise. Okay? So here's what I want you to do. And this is not easy. Define all the various possible other situations that you can think of. Okay, for example, define the limit of f of x as x goes to a equals minus infinity. Write the formal definition for it. Define the limit as x goes to infinity of f of x equals infinity. That's different. But it's a blend, kind of a, somehow putting together the two definitions of x going to infinity and f going to infinity. Think of how you would define it formally. And all other variations, the limit as x goes to a minus of f of x equals minus infinity, etc. You should easily be able to come up with 16 more. Okay, you can go, the x can go to a minus, a plus, or infinity, or minus infinity. So here you have 5 possibilities. And here you have L minus infinity or plus infinity. So here you have 3 possibilities and all possible combinations. Okay? Try a few of these. Try to see that you got the hang of it. Okay? And now there's some shocking news. Remember, when we defined all the previous ones, the bullets on the first board, the definition, whenever there was an L here, whether it was a minus, a plus, infinity, or minus infinity, we said a vague statement of the form, all the theorems hold. Remember we said that? We never quoted all of them again, we never proved all of them again, but we said all the theorems hold. You can sandwich, you can do limit arithmetics, everything holds. Okay? That's no longer the case for infinite limits. Okay? So I want to write that and show you some examples, and that's something that we're going to struggle with and try to find ways to handle in later phases of the course as well. Okay? So remark. For f of x goes to infinity or plus minus infinity, whether you're going to a point or to infinity or to minus, it doesn't matter on what x goes to, not all the theorems hold. Even limit arithmetics doesn't hold. Let's write that. Even limit arithmetics is no longer valid. Sometimes it is, but not always. So you can't use it freely. So let's see some examples. Suppose you have, examples. Suppose you have the function x squared minus 1 divided by 3x squared. That's a perfectly legal function. Okay? X can't be 0, but what I want is, what is the limit of this thing as x goes to infinity? What is the limit of this? It's a rational function. It's a quotient of two polynomials. What's the limit as x goes to infinity? So what's the limit of the numerator? Infinity. As x goes to infinity. The limit is infinity, right? X goes to infinity, x squared goes to infinity squared. No. To infinity, minus 1 doesn't really change anything. So the top goes to infinity. Do you agree? What about the bottom? Also. So this is a situation of infinity over infinity. And never write something like this without quote marks. Okay? So a naive statement would be, okay, infinity over infinity, that looks like 1 to me. Right?
Yep.
But that's not true. So how do you handle a limit like this? You know what to do, right? What do I do? Oof! L'Hôpital is 3 weeks from now, in the future. Okay, we don't know L'Hôpital yet because we don't know derivatives yet, right? Just good old. Right. So this equals, I can rewrite this, divide top and bottom by x squared as 1 minus 1 over x squared divided by 3. As x goes to infinity, that's the limit we're studying here, 1 over x squared goes to what? 0. So what's the limit? 1/3. Does everybody agree? So is it fair to say that infinity over infinity is always 1/3? No. Right? If I put a 4 here, it's going to be 1/4, and I can easily construct an example to have any limit here in a situation of infinity over infinity. Do you agree? Okay? So there's no arithmetics for quotients. Okay? Likewise, suppose you have, for example, in regular limit arithmetics, if you have something that goes to L times something that goes to K, what does the product go to? L times K, right? here's another example. So call this example 1. And here's example 2. Suppose we take x squared times 1 over x squared. And suppose we want the limit as x goes to 0 in this case. Okay? So what does x squared tend to as x goes to 0? 0. What about 1 over x squared? That's the example we just proved. This goes to infinity, right? So this is a situation of 0 times infinity. Now, 0 times anything is 0, right? So 0 times anything is 0 as long as that anything is a number, not infinity. Okay, why? Because what is this limit? This is just a funny way of writing 1. Do you agree? And the limit of 1 as x goes to 0 is, of course, 1. So is it true that 0 times infinity is 1? No. Okay, if you put here a 2, then this is going to be a 2, and the limit is going to be 2. Okay? So the lesson to be learned from all this is that there are many, many situations that we kind of want to do arithmetics, but we can't do arithmetics when, in general, when one or both of the components we're trying to add, subtract, or whatever is infinity. It's no longer true. So I'm going to write it as a remark, maybe, and we'll study this further. We're going to get back to this. This is something we need to handle these limits somehow. So in general, arithmetics does hold for infinity plus infinity. So if you have something going to infinity plus something going to infinity, the sum goes to infinity. Infinity times infinity. If you have two functions that goes to infinity, the product goes to infinity. L times infinity, as long as L is not 0. That will also be true. Okay? So some situations are okay. And formally, you need to prove all these as little theorems using the definition of the limit, the one we introduced today. But many situations we don't have limit arithmetics for, and we say that they're undefined. Are undefined. For example, infinity minus infinity. If you have something that goes to infinity minus something that goes to infinity, it's not true that the difference goes to 0 in general. And whenever I say something is not true, it means that there can easily be examples when this does not hold. So infinity minus infinity, we saw infinity over infinity, 0 times infinity. In fact, maybe we should add to this, this is not an infinity situation, but 0 over 0 is again one of those situations where arithmetics doesn't hold, right? Remember in the phrasing of the theorem of limit arithmetics, we require that the denominator does not go to 0. And if it does, this is again an undefined situation. And there are more. 1 to the power infinity. If you have something that goes to 1 to the power something that goes to infinity, this is not necessarily going to have a limit of 1.
What about infinity to the power 0?
Infinity to the power 0. 0 to the power infinity. Okay, all these need special attention.
0 to the power infinity is not 0?
No. It's not 0 to the power infinity. It's a function whose limit is 0 to the power of a function whose limit is infinity. Okay? All of these, I mean, what's more reasonable than saying that infinity minus infinity is 0? Right? If you just look at this as a symbol, it makes sense, right? But that's not what's written here. These quote marks indicate that what we're talking about is a situation where a function that goes to infinity minus a function that goes to infinity. And in that case, you can have all kinds of things happen. Okay, clear? So we have to be very careful when we have all these infinities in the limits, and we can't just freely do arithmetics or theorems or whatever. Okay? Okay. Yeah. Maybe I'll just quote one theorem that does hold and is useful. And in fact, its infinity version is even easier than the version you're used to. And I'm talking about the Sandwich Theorem. So I want to draw, for intuition, what we're looking at. So suppose this is the point A, and we have a function that goes to infinity as x goes to a. Okay, let's draw a one-sided situation. Okay, I'm not saying it's one. Here's f. So do you agree that f goes to infinity as x goes to a plus? Do you agree? Okay. Now suppose that you have another function, and what you know about the other function is that it's always bigger than f. So here's the other function, g, in orange. G stands for orange. Huh. What can you say about its limit as x goes to a plus in this drawing? It's also infinity. Do you agree? So, and you don't even need to have a third function trapping it from the top, right? The Sandwich Theorem required two functions, the standard Sandwich Theorem required two functions that have the same limit, and then the function that's trapped in between was forced to have that limit as well. Remember? Here all you need is one function that goes to infinity. If a function is bigger than it, it's also going to go to infinity. Do you agree? So let me write the theorem. And by the way, so if you think of that Sandwich Theorem as two slices of bread or your favorite dough kind of thingy, and the cheese in between, sometimes people call this the pizza theorem. Because the cheese is sitting only on top of one layer of dough. Okay? This is not standard terminology in any sense. Okay, so, but let's write it. Pizza. Okay. If g of x is greater than or equal to f of x in a neighborhood of a, in a neighborhood of a. So here the drawing is for the one-sided version, but the theorem is general. And we know that the limit of the smaller one is infinity as x goes to a. Then the limit of the bigger one is also infinity as x goes to a. Well, in the picture I drew a plus, but I want to state the theorem in the general a situation. Okay, you can easily make this draw the other side and have the. Okay, clear? Everybody good? Okay. So this really wraps up what I want to say at this point about limits. This, in no sense, wraps up the discussion about limits. We're going to discuss them a lot, all through this course. But I mean, you still have a lot of work to do to practice all these things and to do a lot of calculations. Those calculations are standard. There are many little tricks there. I'm sure you're going to do a lot of them in discussion and on homework on the MathNet computer homework, and you're going to have some open homeworks to submit. So it's important to know all the little tricks and to do all the calculations. But as far as the theory goes, we're going to stop here and move on to a topic that's going to seem at first completely unrelated. And we're going to see how it is related, deeply related, but it's going to take a bit of time. So what I want to do is let's take the break now so we can start the new topic of sequences at the beginning of the next hour.